Hello, everyone. Welcome to the second DRCC seminar of the semester. Today we have Garv Chauhan, who will tell us about Neutrino Non-Standard Interactions via Light Scalars. To know him a little bit, Garv got his PhD from Washington University in St. Louis, the US, and he's now completing a short postdoc at Louvain University, CP3 in Belgium. And he's also soon moving to the next one in Virginia Tech in the US. For students, the attendance list will appear in the chat shortly. Lista de presença vai aparecer no chat daqui a pouco. So, Garv, whenever you're ready, please take it away.
Thank you, Yarmo. Let me share this. Can you see my screen now?
Yeah.
Great. Yeah, okay, it works. Thank you for the invite and the introduction. And today I'll be presenting about Neutrino Non-Standard Interactions via Light Scalar. So this is a little old work of mine, but it's a very interesting topic, so I thought of presenting it here. So this work is in collaboration with Dr. Babu from Oklahoma State University and Dr. Dev from Washington University in St. Louis. So to begin with, so we know that neutrino oscillations are real, and this also implies that at least two of the neutrinos have small non-zero masses. The neutrino oscillation mixing parameters, which are parameterized by these three mixing angles and the mass square differences, they are now being measured with like subdominant accuracy at neutrino experiments. So the usual analysis of this three neutrino mixing paradigm is performed considering that only the standard model interactions are present and nothing else. But as we know that origin of neutrino masses clearly needs some BSM physics, which will introduce non-standard interactions of neutrinos beyond the standard model. And these might have some observable effects. So since this can in principle alter our understanding of how we interpret the neutrino oscillation data, then it's very important that we quantify and qualitatively also understand the effect of these NSI. So the usual BSM physics always introduces either new fermions, gauge bosons, or scalars for these neutrino mass generations. So neutrino non-standard interaction here written succinctly as NSIs. So either they can be induced by a vector or a charged scalar mediator. Then they are parameterized in this charged current form, like in analogy with the, sorry, this is the neutral current form. So neutral current form in analogy with the standard model neutral current form. And here the strength of the new physics is parameterized by this parameter epsilon with the subscript alpha beta, depending on these two flavors of neutrinos, and the fermion F. And this X denotes the chirality operator, left-handed or right-handed. So this is what is called vector NSI. And this has been studied very widely in literature and is like the main focus of NSI field. But on the other hand, if you have a scalar mediator, a neutral scalar mediator, then NSI that is induced by it then is no longer composed of this vector current form, which is here, but it's actually in this form of this 4-point contact interaction term, something like Fermi theory. So in that case, since it's different, the effects of this term would also be different, as I'll discuss later on. So the prospects of this vector NSI have been studied extensively, but without any much attention to scalar case. So that is what we did in this work. We did an in-depth study of the scalar NSI. So what we did was we considered interaction of charged fermions F with neutrinos through a light scalar phi, where you have some Yukawa terms of the form like this. So we are considering model independent these terms, so you can do some model building around it, and you can find in an effective form you can get interactions like this. We do have a discussion of that in our work, but I will not be discussing that in my talk here. So you have terms of the form nu bar phi nu and f bar phi f, where the strength of this phi interacting with neutrinos is parameterized with y alpha beta, and with fermions with this YF. So in the low momentum transfer regime, we can write the effective Lagrangian term as this 4-point contact interaction term with nu bar nu F bar F. And this strength is given by the coupling of electron and neutrinos to this phi in the numerator and suppressed by m phi squared. So one important thing to notice, that's the main focus of this work, is that in presence of a medium, when the medium in which the neutrinos are propagating is composed of these fermions F, then in that case, this quantity F bar F can be approximated as a function of number density of this fermions F. And in that case, this F bar F can be approximated by some constant value, the density. And then this term is directly proportional to nu bar nu, which we know is the mass term for neutrinos. So yes, in a case of the medium, like presence of medium, this scalar NSI term basically appears as a correction to the neutrino mass matrix. So this was a heuristic way to understand what this term means and what this light scalar does. But to quantitatively calculate this exactly, we will use finite temperature field theory. And one more point that, of course, if neutrino mass matrix is different in a medium, and when we are doing these terrestrial experiments, this can create problems in the determination of our vacuum neutrino masses, as well as CP phase measurements, because they can create degeneracy between the parameters that we are trying to extract. So to use a field theoretic setup to calculate this effect, we use finite temperature Green's function for a free Dirac field. So this is the propagator for this Dirac field in presence of, so first term is the vacuum term, the normal vacuum Feynman propagator term, which you can see here. And the second term actually quantifies the effect of finite temperature of the background medium and density, given here by gamma of P. So this gamma of P is a function of a few different variables that I'll discuss to give you what physically it means. So it's composed of this delta function, which enforces the on-shell condition for this fermions F in the medium, which basically means that the particles in the medium should be real. So it's pretty straightforward. And it's also dependent on these Fermi-Dirac statistics factor, where you have a plus or minus sign for the chemical potential, depending on if you're treating fermions in the medium or the antifermions. And when you sum over all the momentum modes weighted by the statistical factor, you get the number density of fermions in the medium. Here you have a factor of 2 for the 2 spin degrees of freedom. Usually it's replaced by number of spin degrees of freedom for the particle species. So once everything, all the components are there, we can go ahead and write down the relevant diagrams for our case, which are these two important diagrams. One is this, what is called a tadpole term, where these neutrinos interact with the background fermions through the exchange of this light mediator phi. Or you can have these self-energy diagram composed of internal lines with neutrinos and this scalar phi. But usually what happens is if you calculate these effects, the effect of these diagrams are proportional to the masses of the particles that appear inside these internal lines, the ones that are thermalized at least. So in this case, since the internal lines are neutrino and phi, and usually there are very less cases where neutrinos get thermalized, except we know that in the core of supernova they are thermalized, so these diagrams might be important, but usually we only calculate the first term, which is the dominant one. So this term will come to be proportional to m nu. So this is why we are not looking much at it, but we do calculate it in our paper. And if you want more details, you can look there. So focusing mainly on the first one, which is called the tadpole term, you can write down the effect of this term exactly. The mass, the contribution to the neutrino mass matrix in the medium would be exactly this term. So it's proportional to the coupling of this neutrino and electron to this phi times the mass of the fermion in the medium suppressed by m phi square times this particular integral. And this integral is basically, if you calculate it in few different instances, it's just the relativistic number density of particles in the medium, which in the case of a medium which is at rest, where the fermions are not moving very fast, it will just be a function of number density. So to understand better the effect of this term and how the role it plays in different kind of scenarios, we studied for the case, three different cases. So where either the mass of fermion is dominant over the chemical potential and the temperature, or where the chemical potential dominate for the case of, like, say, supernova, or where the temperature dominant, say, for the case of early universe. So we see that this term, this integral, comes out to be proportional to nf to the power 1 for the case of Earth and Sun, since the background medium is non-relativistic. For the case of relativistic mediums like supernova and early universe, we see that this integral comes out to be proportional to nf to the power 2/3. So this is one crucial difference in these two cases. So in the rest of this talk, I'll be discussing constraint on this scenario where these scalar couples to electron. We also have discussion in our paper where this electron couples to, sorry, the scalar also couples to the quarks or the nucleon. So it was originally proposed that large enough scalar NSI can be produced by driving m phi as low as possible. So if I go back to the last slide, this effect can become as large as possible if you make m phi very small. In all these three cases, we see that it's dependent on 1 over m phi squared. So if it's very low, then this effect is super big. So it seems that in presence of this medium, you can, and if you have a very light scalar, you can make scalar NSI as high as possible. That is what was proposed in this original paper by Gay and Park in 2019. And this is what caught our curiosity, and we decided to look into this further. So what turns out is, which was also noticed at the same time by Smirnov and Shu, that it's not, since this is an effect which is induced by the medium, and is the medium that endows the neutrinos with this medium dependent mass. So it's also the medium that provides this cutoff, and the cutoff is the finite size of the medium, because no medium in reality is infinite. So you would not have this happening everywhere at all the time. So a light scalar, how does it provide some natural cutoffs? You can understand that a light scalar that couples with fermion leads to long-range forces. And in the presence of a long-range force, a neutrino that is traveling inside this medium will feel an attractive potential energy from all the fermions around it in a radius of 1 over m phi. It's just the Yukawa force. So once 1 over m phi goes beyond the radius of these, the dimensions of this medium that it's propagating in, this effect gets a cutoff. So basically, then there is no effect for the contribution to this medium mass. So to properly calculate the effect of the finite temperature, density, plus these finite size of the medium, we cannot really all depend on the field theory aspect that I discussed right now. So we start from the beginning. We just solve the Euler-Lagrange equations of motion for the neutrino and phi, and then we go and calculate exactly for the case of finite temperature and density, as well as the finite medium size. So you solve these equations of motion, and then the mass correction at finite temperature and density comes out to be this particular quantity, which looks a little intimidating, but it's, I assure you it's not, and we'll look at it through an example. One thing I would like to point out, we can see directly here that the effects through the coupling of this phi to neutrino, we see that it contributes this particular term in the equation of motion for neutrinos, and this is exactly what induces a medium dependent mass. So in the presence of a medium, this phi, due to the constant value of this f bar f, gets a constant value induced for itself, and this y nu phi also basically adds a finite mass to this m alpha beta, which is the vacuum mass for neutrinos. So now let's look at a special example of this particular quantity to understand it. So It's actually dependent on this quantity f bar f. This particular integral, which is just a rewritten form of this particular integral that gives you the relativistic number density of fermions F. So we consider an example where we have a relativistic medium, although it's not real, but you can consider something like this to approximate it, say in supernova. So for a relativistic medium with some constant electron background density, we calculate this particular integral that I showed you. It comes out proportional to this quantity, which is coupling of this neutrino and fermions with phi times mf over m phi squared times nf to the power 2/3 of the number density of these electrons in the background. And once you see this formula, you remember that we actually saw that previously in our result for supernova here. So we are pretty sure of that now, that this effect gives you, like once you solve this Euler-Lagrange equation of motion, you get this quantum field theory effect there for sure. Times you have these few form factors which depend if you are inside the medium or outside the medium. And these captures the fact of the finite size of the medium. So these will be the form factors that give you this cutoff effect once your mediator mass becomes super low or super high. So these F in and F out, as written here, are given generally in terms of these variables. And for a special case of like where the mediator mass becomes really low, which was the case that the previous paper, that original scalar NSI paper, was positing, this effect does not becomes like, it does not blow up. So what it happens is once you take this limit of m phi goes to 0, this particular quantity Fn over m phi squared takes a constant value, which is just a function of radius of the medium and where you are inside the medium. So if you are at the centers, then it's just r square over 2. And similarly, if you are outside, it takes this constant value and then it drops 1 over r. So this is a pretty regulated effect, and you can also see what happens if the m phi goes to infinity. For that case, the limit is just very simple. For inside, the effect becomes 1 over m phi squared, so it falls 1 over m phi squared, like if you increase the mass of the m phi. And then outside, this effect basically is not present, because what happens is m phi tending to infinity is a limit where the size of the medium becomes infinite. You can basically see it as a point contact interaction term, and it does not feel anything around it. So now I'll be discussing the constraint on this scenario, starting with the constraint on this coupling of neutrino to the phi. So the most stringent constraint that we have on this coupling comes from the time of nucleosynthesis, Big Bang nucleosynthesis, which happens at a temperature of 1 MeV. And then if this is 3, so we are considering first of all for the 3 right-handed neutrino case. So if these 3 right-handed neutrinos and this extra scalar are still in equilibrium at the time, then they will contribute 3 plus 4/7 degrees of like n effective at that time, which is really ruled out because it's only I think the current limits are even stronger, but at the time it was around 0.5. So this would be really in contention if you really want those nu and phi at the time of nucleosynthesis. So what you do is you posit that they decouple at some earlier scale from the standard model plasma, say for example 200 MeV at the time of QCD phase transition temperature, and then they contribute very less at the time of BBM. If we do this, we get a very strong limit on Y nu even then, which is around 10 to the power minus 10. And this is the quantity that I'll be using in my plot for this coupling of this neutrinos to phi. There are several constraints on this coupling of lepton to, especially electron, to this scalar phi. So the first and foremost is that a scalar that couples to electron will contribute to the electron anomalous magnetic moment, which is given by this particular integral. And once you take the current constraints on the G-2, we see that it gives us constraint on this coupling around 10 to the power minus 5 level, where we have On the y-axis, we have this coupling YE, and on the x-axis, we have this M phi in electron volts, since this is a pretty light scalar. And this is for a constant value of this y nu that we got the constraint from BBN. So this is for the case of Dirac neutrino. So this is a pretty constant constraint. So the next very stringent constraint, actually the most stringent constraint, comes from fifth force experiments. So a light scalar that couples to matter, it leads to long range forces, which appears as violation of these equivalence principles that are being probed in experiments. So how these experiments are designed like that, they have basically torsional balances where there is a very thin string and they have two mass suspended on either side of this bar, and then they measure these extra forces apart from gravity on them. So basically they parameterize as the deviation from this Newtonian gravitational potential, parameterized here this extra force by alpha. We know that the Yukawa potential for interaction between matter and a scalar phi is also of a similar form as they parameterize here, and it goes 1 over r and also falls like exponentially dependent on the mass of phi. So if you have, assuming that a particle, either a lepton or quark, that couples to this scalar mediator with a strength q, and if you have an extended body with n number of these particles, then they will contribute n1 times q1 and 2 times q2 to this potential, similarly like just written from here. So if you compare this particular expression with the previous deviation in these equivalence principle experiments, you can find then the strength of this. This is how they report their results in these experiments. So that's why we are trying to convert back to the quantity. So this alpha is parameterized by this mainly by this ratio q1 over a1, q2 over a2. For the case where we want this coupling strength is proportional to lepton number, because an electron is coupling to phi, so basically it's proportional to lepton number, or just say the atomic number. Q equals z times ye. So once you replace this q1 and q2 by the test mass and the source mass between which you are trying to measure this extra force through this light scalar phi, you get this strength of alpha, which is basically dependent on the ratio of this atomic number to the mass number. For the case, if you want coupling to nucleon, you will actually find that you have to replace this q1 and q2 with the baryon number. And for the case of baryon number, this is actually proportional to just the mass number of the two test mass and source mass being used. And in that case, those ratios are independent of the materials being used. So for the case of coupling to nucleons, this effect is actually independent of the materials being used in the experiment. So once you have all those experiments, there are quite a few, and they have very strong bounds on this coupling by E. So they are around 10 to the power minus 20 to 10 to the power minus 24 levels. So there are several of them that were done like in past 50 years. So they're like numbered 1 to 7. Plus you have these torsional balances experiments. So these are one of the strongest bound on this quantity. Moving on to the next one, we have similar constraints from BBN on this coupling YE. So because if this scalar mediator phi is in thermal equilibrium with the standard model, then it can lead to this kind of annihilation type process where this phi can be produced, or this Compton-like scattering process with where a proton striking an electron produces a phi on the other side. So if this phi enters equilibrium with electrons before the time of BBN, then it can decrease the deuterium abundance, which will be in conflict with observations. So if this mediator thermalizes and decreases the deuterium abundance, if it's the thermal average cross section is greater than the Hubble rate at the time of BBN. So this pretty much yields a very strong and almost constant bound for this ultralight scalar mediator around 10 to the power minus 10 level, which appears on the plot stronger than the G minus 2 bound over here. So the next one is the constraints from these astrophysical bodies, which are namely red giants, horizontal branch stars, and supernova 1987A. So what happens is, if you have a very light scalar phi, then which couples to these electrons, then it can be produced in these scalar bodies. And since it doesn't interact much, it has a very long mean free length. So mean free path length. So then what happens is it leads to a new channel for energy loss, which leads to rapid cooling of these astrophysical bodies. So for the case of red giants, it can delay the onset of helium ignition if it takes away too much energy. For the case of horizontal branch stars, it can change the helium burning lifetime. And for the case of supernova, what happens is, since we have measured the number of neutrinos and we can reconstruct back the amount of energy loss from supernova 1987A through these neutrinos, we have an upper bound on, we have almost an estimate on how much energy should be released in this neutrino burst. And it's pretty consistent with what we think our model should do. So we have stringent bound if a phi couples to these electrons and lead to another channel. So this is like a lower bound, which will be set on these couplings from this condition. But for the case of supernova, there is another interesting bound, that for the large values of coupling, the scalar can actually get trapped inside supernova, and then in that case there are no bounds on this coupling above a certain value. And this happens because if it gets trapped, then there is no energy loss, and then you cannot use the previous reasoning to put a bound on that coupling. And you can find it by calculating the mean free path length, and if it's smaller than the size of the supernova, like this proton neutron star that is formed after the explosion, then the bound on coupling YE can be derived. So for the case of red giants and horizontal branch stars, we see that it's a pretty stringent bound, and it's applicable for all cases even above this coupling. But for the case of supernova 1987A, we see that it's stringent for the case of 10 to power minus 9-ish, but it vanishes away when you reach for the case of 10, when you are at the level of 10 to power minus 7. So we see that for the case of supernova 1987, it's a small band, but they're already pretty stringent constrained from the case of BBM. So we do not really get any space there. So next, if you have, these were the constraints for the case when this phi couples to the electron. Now for the case of nucleon, coupling to this phi are pretty much the same, except that the G-2 bound is actually kind of replaced on a similar level from the meson decay bounds. So what happens is, if you have a scalar phi which can be which couples to these nucleons, then or at the quark level couples to quark, and then this can be produced through a decay of these charged kaons. And this process, this rare decay process of like this charged kaon going to pi plus to missing energy, is constrained from the measurement of these cross section of this branching ratio of this charged kaon to pi plus nu bar nu. So it's pretty constrained. So we see that the production cross section can be written in this form, and you can get bounds on this from the measured values. So if you write a Lagrangian on a nucleon level, you can convert back and forth to the quark level coupling using these nucleon scalar charges, which are calculated from the lattice calculations. So these were the theoretical constraints that we were discussing on these quantities from current measurements, but they're also on this coupling directly on YE. But there are also bounds on the experimental value of this maximum scalar NSI that can be produced, like the maximum size of these medium masses of these neutrinos. So there is a bound from the analysis of the solar neutrino data, which comes from this chi-square analysis of the Bourg-Zeno data, which sets a 3 sigma upper bound that this scalar NSI in Sun cannot be greater than this 7.4 milli electron volt level. And also there is a similar constraint, but far larger from the case of supernova, that which comes from the fact that if the scalar NSI in supernova becomes too large, even larger than the typical temperatures that are present in supernova, then these neutrinos will not even be produced in the processes in supernova. And so basically it would mean that we should not have seen any signals from supernova 1987A. So, but that's not the case. So we can set a upper bound on this value, which is around, for typical value of supernova temperatures around 30 MeV, we can set around 5 MeV. This is a heuristic value. This can fluctuate a little bit, but for proof of principle, this kind of holds. So these are all the constraints that I've discussed until now for the case of this phi coupling to electron. You can see the experimental constraints from supernova greater than 5 MeV are around this level. They go like this. And for the case of sun, they are even stronger and rule out a little bigger parameter space in this coupling region. Now, before we move on and see what actually are the NSIs that are possible in case of Earth, sun, and supernova, I would like to discuss one last limit that is applicable for the case of when the fermions in the medium are bound in a bound state. So what happens is, for the case of early universe and supernova, all these fermions in the background that we were considering, or even in our calculations, they were free particles. But in the case of Earth, it's special that they are bound states. They are in form of molecules, atoms. So if our neutrino is passing through Earth, then it will scatter off these atoms. So what can happen is it can scatter off these electrons in these atoms and can, instead of the recoil energy being enough to shoot it out of the atom and us measuring that recoil energy of the electron, it can again get trapped back into the same atom. So it can just jump from one energy state to another. So consider this electron neutrino elastic scattering and working in the rest from the electron. We can calculate that this q square, this momentum transfer related to this coherent forward scattering of neutrinos, is of the same order of these electron recoil momentum. So P is the recoil momentum of this electron. So since this recoil momentum of the electron is subject to uncertainty relation within the boundaries of this atom, so heuristically you can estimate that the bounds on these delta q square, which is proportional to this p square, you can calculate here, is of around 14 eV-ish. Like q is about 14 eV-ish. So what happens is, if your mediator mass kind of goes below this, or like the momentum transfer is below this, because in that case, this effect becomes kind of independent of the mass of m phi in the case of bound electrons. So I'll show you that as an example in the plot. So when basically mediator mass falls much below this particular momentum transfer scale, then one should just use the quantum mechanical cutoff. So basically the denominator in the propagator is mostly dominated by this momentum transfer of this 14 electron volt square rather than the m phi squared, which we were earlier calculating for. So we see it's the same plot that I showed you earlier with all the constraints in, plus the scalar NSI plotted for the case of Earth. So we see that it comes pretty directly straight from this direction for m phi around 100 eV. But there is a sharp turning point around this energy scale, which actually happens at the 14 eV-ish scale that it is discussed. And what happens is, once your mass of the phi drops below this momentum transfer scale, then basically this effect becomes independent of the mass of m phi. And this kind of only happens for the case of this particular quantum mechanical bound. Moving on to the case of sun, we see that this effect is proportional to m phi for the case of large coupling and large mediator masses. And in the naive case, where you would not take into account the finite size of the medium, you would expect that this line would just straight go down and can be so it can be as high as possible because it's a constant contour lines for the scalar NSI, but the couplings and the masses can be low. But what happens is, since the finite size of the medium provides a cutoff, provides a cutoff. This particular effect has a scale where it becomes constant and independent of the mass of m5. And this happens exactly at the inverse size of the medium. So when m5 becomes 1 over r, the size of the medium, which for the case of sun is around, for the case 10 to the power minus 16 eV. And for the case of supernova, we'll see that it would be around 10 to the power minus 11 eV, which is in kilometers, which is around 10 kilometers, the characteristic scale, the usual length of the supernovas. So we see that for the case of sun, the highest possible scalar NSI is around 7.4 milli-electron volt if you have smaller masses and smaller couplings. But more realistically, if it lies around this side, then it will be pretty small, because if you see that this is 10 to the power minus 5, and it will be around 10 to the power minus, I think 10 or even less. So if you have any realistic chance of measuring, it would be around here. For the case of Earth, I forgot to mention that it will not be measurable by any future or even future experiments, because you can see that the effect of this delta M Earth, if measurable or if allowed by current constraints, is around 10 to the power minus 17 EV. So this difference in the neutrino masses is not measurable by any chance, and even this part is around 10 to the power minus 10 EV. So there is no chance to measure the scalar NSI in Earth, even if it exists. Moving on to the case of supernova, we see that for the case of supernova, there is a small region where it can be as high as 5 million electron volts. But if in this region, it's most likely around 100 electron volts or 1 electron volt, around this range over here. So to conclude my talk, I presented that this neutrino NSI with matter mediated by light scalar induces medium dependent neutrino masses. Generating these observable effects for these scalar NSI requires an ultra light scalar mediator, but the finite medium size provides a natural cutoff for this effect, where you would expect that this effect can be as large as possible, since it's suppressed by 1 over m5 squared, but that's not the case. So we analyzed long-range force effects, as well as we gave experimental constraints from these terrestrial, astrophysical, and cosmological domains. And although these observable scalar NSI effects are precluded in terrestrial experiments, that they would not be seen ever, but they can still be probed in future solar or supernova neutrino data. Thank you.
All right. Thank you very much, Garv. Any questions?
I have one.
All right.
In the equations of motion, couldn't the Yukawas have also the indexes like alpha, beta?
You mean for the YF?
Yeah, for Y nu.
Oh yeah, oh sorry. So they can technically, yes. So if you do properly, yes, they do. We are considering here, like, since we were considering like this flavor diagonal even for neutrinos, since we wanted to display. So yes,
Okay.
in technicality they can, yes.
Okay, so but you are considering only flavor diagonal.
Yeah, like for the plots we have used flavor diagonal, but the results that we have derived, they are like applicable to all of them.
Okay, so if I put like the indexes and so on, I wouldn't change much, like those limits you found, those lines.
No, I think the limits on these off diagonal terms in this one. So what happens for this particular term? What happens is, like, this actually goes away. Like since this is proportional to the number density of neutrinos in the medium, which if they are not thermalized, it will kind of go away. So this term really does not contribute in medium if it's not. But I'm suspecting if you, for example, say supernova, there they are thermalized. So there, this kind of term might be important if you're looking at this scalar NSI effect. So yeah.
Okay, thanks.
question for Garv?
Thank you.
So another question then. So if the mass of the mediator is less than 5 MeV, then you don't affect neutrino production. That's what you said.
I think the audio was not clear. Can you repeat?
If the mass of the mediator, you put like delta MSN less than 5 MeV, then you don't alter like you don't affect like neutrino production in the.
Yeah, so it's of course, if you do the neutrino transport and something, I think you can even put a stringent bound inside supernova. But like just realistically thinking, okay, if they are heavier than 5 billion electron volts, then there is not even enough energy in supernova processes to produce them. And if they are not produced, then you would not see them. So basically, if they're medium masses is too high, then you don't have them.
Okay, but they can. I mean, just curious. Like, let's say if they are like 5 keV.
Okay.
Would they affect like the neutrino production, like the amount of flavor, for example, the amounts of nu E bar that are produced, or you don't know?
I think neutrino transport will be changed, but I think production can be only changed if you have, I think, flavored off diagonal terms, I think, because otherwise it doesn't do much, like
okay,
you know, because if they're flavored diagonal, they basically it's just a mass term for them. Otherwise, if you have off diagonal terms, then basically you are having your flavor converting from one to other. Then might be some interesting stuff.
Okay. Okay.
Thank you for.
All right. So, anybody like to ask
a question, William?
Sure.
Thanks for the talk, Garv. Just to understand the figure in slide 30, the question is if the bounds are statistical ones, and if yes, what's the significance?
Which one?
Yeah, all of them, actually.
So the significance, I will overall say, if you keep in hindsight that it turned out that you cannot see it in Earth, like turns out like sometimes even if you don't have an effect, you can put you don't have an effect, you can put some bounds on the coupling itself, like so you wouldn't have these light scalars roaming around with these, at least these values, like in any model or something. So as if for this scalar NSI, even so, if it exists, of course, it should be somewhere around here. But even if it's not, then you can at least, you thought of another kind of effect, this medium dependent neutrino masses that should arise from them. And then you can constrain these kind of couplings, I'll say. If you're asking for the significance. If you're asking some questions, especially from the slide, I can answer in specific, maybe if I didn't understand correctly.
Okay, no. It's okay. Thank you.
Thank you.
Oh, I think what he was asking is about like this 90% confidence level, 95, this kind of thing.
Yep.
Oh, so other ones are like just proper constraint. Like they have some values for these things. They shouldn't be for that. I think for if you are thinking about 90% confidence, this is like a 3 sigma range for this delta M sun. I think that is the only one that is you can ask about confidence level, because other ones, like for this supernova one, it's a heuristic bound like 5 MeV. Like it can have maybe a little bit scatter over here to here, but you will need to like calculate it properly, like how much. First of all, there is a scatter in the temperatures of supernova and other quantities. So for example, this one cannot say for sure how much would be the scatter for this, like how much. And for, yeah, other ones, they are just like, I think, yeah, 3 sigma bounds on the quantities, however they must measure.
Okay.
Thank you for the question.
So, any more questions? So I actually have one. That blue region, that G-2 for the electron,
Yeah.
then if you show the same plot for muons, then maybe can you explain the G-2 for the muon?
If you're considering muon coupling to phi, I think, yeah, then you'll have that line, yes.
Okay.
Actually, for electron, it's very strong, by the way, because it's because the allowed G-2, this delta G-2 is basically in opposite direction to the muon one. So you have to, I think, consider like 5 sigma region for this one to actually not rule out this scenario totally for the case of electron, I'll say.
Oh. All right.
Because a scalar contributes positively to this G-2, and so but the deviation is negative, like the 1 sigma deviation is just negative. So you have to consider few sigmas deviation from that to actually go to the positive region and then put a bound on this coupling. Otherwise, if you take this the negative 1 sigma result, then yeah, so then it's pretty strong. Whole scenario probably gets ruled out. For a muon, I think it would be easier.
Uh-huh.
Nice question.
So
I think also adds to Marco's question too. Or Gmail.
So the best place to look for this scalar is in the 10 to the minus 10 EV.
Yeah, I think this region is a good one. Maybe in solar or supernova. Maybe supernova. It does something in the transport, I'm guessing, because you cannot really measure so far away from supernova. But yeah, transport properties might be changed. My guess. People do study this quite a lot of time.
This for a scalar that doesn't mix with the Higgs or mix very little with the Higgs.
I think that depends what kind of model you build. So I think it depends. I think trivially should, I think.
Yeah. Okay. Thanks.
Thanks.
Can you hear me?
Yes.
Yes, I can.
Oh, I have one question. So first, thank you for the talk. And my question is regarding these last constraints that you showed. I didn't understand it exactly, how you put these limits. Could you explain it again?
Which one? These two or all of them? With
The ones regarding the sun and the supernovae, the last ones
oh,
that you showed.
Okay. So okay. I think I'm so sorry. These are like kind of not constraints. They are so the constraints from the sun and supernova are only from here. The other ones are like just projected lines if the scalar NSI is around.
Okay. So if you have this mass difference, so you are looking for this coupling, this mass. Is that you are showing?
Exactly. So if it's like around 10 to the power minus 5 EV level, then you will see that the allowed region is around this area. This is like just projections of those quantities. I should have mentioned that. Thank you so much for
okay.
that. Yeah, thank you.
Okay, thank you.
All right. You have time, people. You can ask more if you want. Yeah. It's
sorry, I lost a bit the question of Pedro. So these black and blue lines are not constraints. They are just like you are giving an example. If the mass was this one, this would be the, okay.
Yes, that's exactly what it is. Yes, I should have said that clearly. The only bounds are actually these, the one from delta M sun, which are like this colored side on this side, and this delta M sun, because these are like the maximum. This one is from the Borg-Zeno data. This one is from like heuristic argument that it would not be produced. So yes, this puts the bound. All of this colored part is the bound, and then these are just projections. So this is for the case of sun, like optimistic values lie around 7.4 electron volt if it's nearly grazing around this area, and around, so if you look a little further from that, it's around, these values are around 10 to the power minus 5 electron volt, just to give a feeling of the values that will be produced here. So for the case of supernova, here it contributes like 1 electron volt mass to neutrinos. Here it's like 10 to the power minus 2 eV, so it goes similarly in these contours. And turning point always happens at inverse size of the medium.
Okay. It would be the sweet spot to look for it now, this region.
Yeah, sweet spot would be this, because it's like it produces the maximum and it's not, and it's the highest couplings in the region. So this would be a good spot.
Okay, got it. Thank you.
Thank you.
Yeah. All right, everyone. Thank you for coming, and thank you very much, Garv, one more time for this nice talk. And I think we're done for today. And well, see you next week, people. All right. Thank you.